Okay, good morning, everybody. So today we'll share with you the chapter on observed disk demographics of young stars at their protoplanetary disks and what they can teach us about disk evolution and planet formation. So this is the full list of authors. The chapter was led by Carlo Manara. The co-authors included myself and Giovanni, of course. Jonathan Williams is also here this week. And then in addition, Meredith Hughes, Phil Armitage, and Giuseppe Lodato, who were not able to make it this week. So in terms of the talk outline, I will go over the observational side of things, and then Giovanni will take over to cover the theory, and then we'll compare the theory to the observed demographics. I will note that the chapter included significant discussions on debris disks, but we didn't have enough time in the talk to cover that, so apologies to Meredith Hughes, wherever she is. But go look at the chapter if you're interested in that phase. So to be upfront about the topics that are not being covered in our chapter, we don't cover disk gas masses, and that's because the detection rates in the ALMA surveys of the CO isotopologues were really low, so we just didn't have the numbers to do demographics. And as we heard in the previous talk, there are still a lot of issues around abundances and things like that of the gas molecules and how that's converted to gas mass. The other thing that we don't cover is disk substructures, and that's because the ALMA surveys were what was then considered high resolution, but now moderate at about tens of AU. But that is covered in a chapter that we heard about yesterday. We also don't cover environmental impacts, so we do not consider binaries, but you can look at the chapter 8 and also a recent review that's out on that. And we also don't look at external photoevaporation in this chapter, but that shouldn't be too big of an issue for the disks that we look at in nearby star-forming regions. But you can look at chapter 4, and also there's another really nice review that was recently out on that topic. Okay, so let's look at the observations. To do that, we can go on a trip down memory lane to the before times of PP6, when disk demographics were basically, in large part, just based on SEDs. So we didn't have fancy galleries of beautiful images of disks or really impressive spectra. We just had good old-fashioned broadband photometry. And it's limited in what you can learn from an SED, but what's nice is that you can get that information very quickly for large numbers of sources. So you can use these to say something about stellar mass, albeit perhaps not super accurately. But the thing that's really important here is that SEDs are very good for efficiently detecting the presence of a disk around a young star, and that's what's being shown in the schematic. And like I said before, you can do this for large numbers of sources very quickly. And when you do that for all the disks you know in all the star-forming regions you know, you can plot, for example, the fraction of the disk frequency as a function of age of the cluster. You can fit a curve to that. And in this case, it's showing us that the disk half-life is very short at about 2 million years. So that's great. And if you fast forward 10 years to now at PP7, the disk demographics have evolved to now be these moderate resolution surveys in the millimeter, most notably by ALMA, of course. And then also paired with that, surveys that use broad wavelength spectroscopy. And the real workhorse here has been VLT X-Shooter. And this covers all the way from the UVB through the near infrared. So when you have this type of data, you can now say things not just about the fact that a disk exists around a star, but as we've just heard a lot about, you can start saying things about how much material is in that disk and is available for planet formation. With the spectra, you can not only get much better estimates of stellar mass, you can also start getting accurate measurements of stellar mass accretion rate. And when you combine those two things, you can start to constrain things like disk evolution processes and planet formation timescales. Okay, so let's take a look at the millimeter disk surveys and how they've improved since PP6. So this is a figure from the chapter, and it's showing where we were in around PP6, which was also around ALMA cycle 1. So we had a handful of millimeter disk surveys, and the sensitivity was hovering around 10 Earth masses, if just looking at the dust mass. If you go 10 years up until now, you see a very significant decrease in the detection limits by up to 2 orders of magnitude, so getting down to 0.1 Earth masses in the dust mass sensitivity in some cases. And then just the flurry of ALMA disk surveys that we've seen really has upped the count for the number of sources that have been observed to sensitivities about an Earth mass or less. So we've gone from just a handful to about 1,000 at this point. So very significant improvements in terms of the millimeter surveys. We can take a look at a very similar thing in the spectroscopy side for observing the young stars. So 10 years ago, we were only looking at a couple regions, and the mass accretion rates limits were not that great. But now we have basically tripled the sample size for that, and we've improved the sensitivity by about 2 orders of magnitude for the mass accretion rates. So lots of improvement on that side as well. Okay, so one of the main products, I think, of this chapter is a table that is available online with the chapter, and it's a uniform sample of disk and star properties in the nearby star-forming regions. And we really hope that it'll be very useful to the community, so the link is there for the chapter. Please go download the table and use it and give us feedback, because we really want to make sure that it's very useful for the community. These are the regions that are considered in the table, and then the references for the ALMA data and the X-shooter data in most cases. And the sample of the table up there is showing the properties that we derived for the star and the disk, but the table itself contains a lot more information about the observations. It compiles Gaia distances. It provides stellar mass estimates for different pre-main sequence evolutionary models. So there's a lot more in there. So if you don't like our assumptions of how we calculated things, you can recalculate them yourself. Okay, I'll very briefly go through how we derived these disk and star properties. Thanks to Ilsa, I do not have to go through this at all. But you can see we made all the assumptions that everybody complains about. But if you're going to do this for 1,000 stars, this is kind of what you have to do. So what we did was we took the ALMA flux from the literature, and then we calculated it in a uniform way, assuming the same dust temperature, grain opacity, and things like that. And then we used the updated Gaia parallaxes for the distance. For the disk radius, we just took them from Hendler 2020. They were great because they already did the uniform rederivation of the radii. So they just fit a nuclear profile to the ALMA visibilities in the continuum, and then defined an effective radius that contained a certain amount of the total flux. So we just took that from the literature. For the stellar properties, so this was mostly taken from X-shooter data, and I'm not going to go into detail about this, but it's very nicely laid out in the paper, all the advances that were leveraged in terms of not just the new data, but also improvements in the modeling as well. And we also rescaled things to the updated Gaia distances for this as well. Okay, some caveats on the sample selection and completeness. So we only looked at regions that were less than 300 parsecs away, and the reason for that is because you could get dust mass sensitivities about an Earth mass or less. And then for the stellar properties, you could get things down to the brown dwarf limit. So it provides a really nice uniform sample. The completeness for each of the regions is going to be about 80 or 90% or better, and the reason for this is that the disk surveys were done based on the Spitzer survey maps, and these regions were around the molecular cloud cores. We now have Gaia, and we now know that there are members that are off the cloud cores, so there are some missing, and there's work done to now get those completenesses back up, but that's why they're not at 100%. And then finally, Taurus, last time I checked, is still in the northern hemisphere, and so that's a shame because it's really difficult to get with ALMA. We can't get it with X-shooter, and so we include Taurus in the sample, but the observations are not up to par with the rest of them. The disk masses are from pre-ALMA surveys. We have stellar masses, but not a lot of mass accretion rates, so just something to keep in mind. Okay, so we have all those wonderful observations now. What do we see in terms of trends and correlations? We saw this equivalent plot in the previous talk. So it's a cumulative distribution plot of the disk dust masses. And it takes into account upper limits, so that's why the distributions are not going all the way to 1. But as we've discussed in the previous talk, you see this decrease in the dust mass distribution with age. And if you believe the dust mass calculations, you see things go from about an average of 15 Earth masses down by a factor of 3 to about 5 Earth masses in dust. But again, this is not accounting for example, if there are things that are greater than centimeter in size and things like that. There are some regions that do not follow this general decrease in dust mass. I'm highlighting Ophiuchus here. It's an interesting case because it's one of the youngest regions that we've surveyed. And for some reason, it has a dust mass distribution that's actually lower than regions that are slightly older, like Lupus. So this could be different initial conditions. This could be more complex star formation histories. It could also be, an interesting case would be secondary dust production. So after a few million years, collisions by planetesimals will actually create a secondary dust population. And so you get a bump up after a few million years. Another trend that we see is the positive correlation between disk mass and stellar mass. So this was seen pre-ALMA in Taurus, and now it's well established in other regions. If you look at that line in the plot and think, wow, that really doesn't look like it fits the points, it's because it's using a method that takes into account error bars on X and Y, and also upper limits, so it can be a little non-intuitive looking at it. But the slopes of these can be compared to each other. The younger regions typically have very similar slopes, and then at upper SCO you see a potential steepening with age. For all the regions, you see the same pretty large spread of in disk mass at a given stellar mass. That's observed for all regions, so that's interesting because it implies that it's something intrinsic to the dust population. It's not due to environment, for example. In the chapter, we threw all the star-forming regions together and put it on this plot, and you'll see that you can't really see the correlation anymore. And that's likely because of, one, the large scatter in the relations that I just mentioned, but also that decrease in overall dust mass of the population that was in the previous cumulative distribution plot. Looking at the stellar properties, so this is, there's a correlation between mass accretion rate and stellar mass. This relation has been long established, but with the newer surveys that use X-shooter data, you can really reduce the error bars on these properties, and what was shown is that the large spread in mass accretion rate at a given stellar mass still remained, even though we were getting those observational uncertainties down. So it seems like that spread is something that's a physical property of the populations, and importantly, it's several times larger than what you would expect in spread when considering accretion variability. And again, if you throw all of these star-forming regions together into a plot like we did for the chapter, the correlation remains, and that steeper than linear slope remains as well. It's about 2 in this case. So the reason why this correlation exists and the spread and everything like that is still unclear. On the theory side, there are many papers that look at potential for initial disk conditions, and also many papers that look at this being a result of disk evolutionary processes. So the jury's still out on that. So now comparing the star and disk properties, this is mass accretion rate versus disk mass. And really thanks to the ALMA and X-shooter surveys that could really get more sensitive observations, this was able to be shown to have a near linear relation very clearly for the first time in recent years. And this relation is really thought to be intrinsic. It's not because both of those are dependent on the mass, the stellar mass, for example. And there seems to be, again, a pretty large spread around the 1 million year line when you take the ratio of those two properties. Okay, so lastly, for the observations, we see a correlation between the radius of the disk and the millimeter luminosity of the disk. So this was seen pre-ALMA, and now we've seen it in other regions as well. The slope is sublinear in the younger regions, and then it becomes even shallower for the older upper SCO region. And you also see a decrease in the disk size when you get to upper SCO as well. So this could be due to optically thick substructures in the unresolved inner regions of the disk. That's one hypothesis for this. And related to that, it's important to note that this disk radius is the dust, right? So we've heard in the previous talk as well, the dust is obviously affected by other processes that can then mess with what we actually observe. So we're hoping to get more radii in the gas, but it's more difficult to do. And with that, I will hand it over to Giovanni.
All right, thank you, Megan, for introducing the observational side of things. And I'll now try to put all of these into the context and the framework that we use to understand the disk evolution. So as usual, I go back to PP6 and see where we were back at the time. And at the time, there was basically one framework that we tried to use to understand disk evolution, which was the viscous framework to explain why disks accrete, and so to explain, the classical problem of how to get rid of angular momentum in the disk and eventually lead material to accrete. And then we thought that this dispersal was mainly due to photoevaporation. And so this led to the sketch you see here on the left, where we had a full disk accreting onto the star led by viscosity. Eventually, photoevaporation would open a cavity, a gap in the disk. The inner disk would be completely removed by photoevaporation, and you would be left just with the outer disk that eventually would be dispersed. Now, as Mario reminded us this morning, actually, already back at the time of PP6, there were already problems with the viscous picture and the MRI. But as usual, those things tend to take some time to diffuse from the pure theory to the application to observation. So these had not been done yet at the moment. And back then, the focus was really how to constrain, essentially, the model parameters of this framework and try to understand how big was the viscosity, what was the photoevaporation rate as a consequence of the different heating and cooling mechanism of the gas. Now, where we stand now, a few years later, if you want, is actually more complex than that. You could say that the problem has actually become more complicated, and that's because the viscous picture is not clear it's actually the right one, as we heard from Mario earlier this morning. And so actually now even which framework we should use to describe viscous disk evolution is not clear. It's still an open question. We still have the kind of classical old picture of viscously driven disks, but we also have the picture in which instead disks evolve because we have winds launched by the magnetic field that are taking away angular momentum from the disk. So if that makes you a little bit sad to see that the problem is more complex, at least if it is any consolation, you will appreciate that at least the quality of the cartoons has improved in the meanwhile. But jokes apart, many thanks to Phil that has done all the sketches that are in our chapter. Right, so I won't enter, of course, inside all the theory that is behind all of this, because Mario already talked about this earlier this morning, but I'm just interested in highlighting a couple of things in the qualitative evolution and how this is different between the two frameworks, how we expect it to be different. And in the viscous picture in particular, it's clear that because we just redistribute angular momentum radially throughout the disk, we conserve it overall, the disk must expand. So this yields a very clear observational prediction, actually, that in this framework, the disk should get larger with time. If you think instead that accretion is driven by winds that take away angular momentum from the disk, then you should not expect any expansion of this sort. So the disk should either become constant, remain constant in time, or actually should even shrink with time. So that's a qualitative difference that you expect between the two models. Of course, you want to make these a little bit more quantitative. So you want to have some kind of simple models that you can use to compare to the observations. And for the viscous model, this has been around for a really long time because those are the solutions, the classical solutions by Lindenbell and Pringle. For the MHD wind case, actually, those solutions were not really much around back at the time of PP6. But in those years, there's been a lot of development of this side, and now we have simple 1D evolution models that can tell us how the disk evolves over the time scale of millions of years. And you see here some examples. For example, here we have a comparison between the evolution of a classical viscous disk, where the disk mass is going down and the disk is also becoming larger with time, and the one of just a wind-driven disk where the size instead is completely constant and you're just removing mass through accretion. Of course, a point to make here is that those are highly idealized models compared to all the complexity that we expect from the actual physical processing happening in disks. But still, the hope behind these models is that they catch correctly the qualitative features of disk evolution, and that's why they're still useful in comparison to observations to try and make sense of what we are observing. There is another qualitative feature that I want to highlight before actually moving to see how we can explain the observations we have, which is what you see here. So what I'm plotting here is a function of time for the two models, for the two frameworks. This quantity, which is the ratio between the disk mass and the mass accretion rate onto the star. So now, a general feature of viscously evolving disks is that, as I said before, they spread. And because they spread, the material moves to larger radii, where all the evolutionary time scales are longer. And so any viscously evolving disk will have its evolution slowing down with time, because everything moves to larger radii. So that's really a consequence of spreading that you will always have. And so this quantity, because dimension is a time scale, means that this quantity must increase with time as the disk gets older. And actually, you expect to establish a quasi-steady state where this quantity is comparable to the age of the system. Now, what I want to highlight is that you don't have anything like this in the MHD wind-driven case instead. Because you don't have spreading, you don't have this expansion, and so you don't expect the establishment of this quasi-steady state. There's another consequence of this, which is that because the evolution slows down, in the viscous case, you will never get rid of the disk. And that's why classically, if we want to explain also disk dispersal, in the viscous framework, we need to couple it with photoevaporation, because we need something that takes away mass from the disk. Instead, in the MHD wind case, we don't have the slowdown, so actually MHD winds are capable also of dispersing the disk, as well as explaining why we see accretion onto the star. Okay? So this will become important now, where we try and see how these frameworks compare to the actual observations we have. So, as I said, in the viscous framework, we expect the establishment of this quasi-steady state, and this means that we expect a correlation between the accretion rate and the disk mass. And that's one of the correlations that indeed we see, as Megan just reminded us, in the data. We have a clear correlation between the accretion rate and the dust mass. And the normalization is more or less the age of the system, the age of those young stars. So actually, that was an early success, if you like, of the viscous evolution framework, which put some confidence that maybe the framework was still kind of okay. But actually, things are a bit more complex than that, and that's what we realized when we moved to older regions. And that's because the viscous framework also predicts reduction in the spread around this correlation, as a consequence that everything tends to this steady state. And you see it here on the right from synthetic populations, where as time passes, all the synthetic data points tend to converge more on the solid lines. Now, this reduction in the spread is not observed. And the other thing that is not observed is also that you should expect the normalization of this correlation, which again is an age dimensionally, to change with the age of the region you're looking at. And also this is not observed when you go to older regions like Upper SCO. Actually, they tend to have similar spreads and similar normalizations to younger regions like lupus. So that's actually a failure of the viscous model. You can still rescue it if you invoke dust evolution, which tends to decrease the dust masses, because through radial drift, we lose dust onto the star. And that means that the actual masses of the disks are actually higher than what we measure from the dust, as was reminded already in the previous talk. But I should point out there is an explanation that at the moment has been worked out only for the case of smooth disks. And so there is some interplay here with the case of substructure disk that is still to be explored. And so it's still not clear if overall you can still rescue the viscous scenario from this point of view. If you move to the MHD-WIN framework, actually, we can show that this can reproduce the correlation that is observed. And you see here some population synthesis exercise that was done by Benoit Tabon, where he was able at the same time to explain both the decrease of the disk fraction, so disk dispersal, and also the correlation between the accretion rate and the disk mass. But the point to make here is that a difference with respect to the viscous framework is that while a correlation in the viscous framework you always expected, it's universal and you should always get there, in the MHD-WIN framework, you don't expect it because you never have this quasi-steady state. So what this means is that you can still reproduce the correlation you see in the data, but to do this, you need to pick the right initial conditions. So it's not universal. You can say it's actually a good thing because it means you have some constraint on the disk initial conditions, whereas in the viscous framework, the existence of a correlation does not tell you much about the initial conditions of disk evolution. The advantage of the MHD-WIN framework here is that it's actually compatible with the constant spread and the normalization with age that we observe. So this is maybe a mild success, let's say, for the MHD-WIN framework. For what concerns then the other correlations that we observe in star-forming regions, which is the correlations of the disk mass and the accretion rate with the stellar mass, those are less universal in a way, as Megan just said before. So it's not clear whether those are consequences of the initial conditions or whether they are a consequence of disk evolution. And so in this way, that's the reason why you can't use them to understand which of the two frameworks, the viscous one or the MHD-WIN one, is more correct. But that being said, I want to highlight that they can still teach us something. And I'm just going to make here one example of what we can learn from them. So if you believe that one of the two frameworks is correct, for example, let's say that the viscous framework is correct, then you can still learn something about how the parameters of those models scale with the stellar mass. And that's what is in this plot. So say, for example, that the viscous time scale is the same for all the stellar masses. Then what you expect in this case, if you have some disk masses as a function of the stellar mass at a given time, if you let time pass and the viscous time scale is the same everywhere, well, then you just expect an homologous depletion everywhere. So in this case, the slope of this correlation will not change with time. Now imagine instead that you have a different case in which at low stellar masses, you have shorter viscous time scale. Then what will happen in the same time step is that actually this decrease of disk masses here will be larger than the decrease in disk mass at higher stellar masses. And so the correlation will tend to become steeper with time. And because this potential steepening in star-forming regions is actually observed, for example, this implies that for the viscous framework, if it is correct, then the viscous time scale should be shorter for low mass stars. And so you have a correlation that is inferred from this between the viscous time scale and the stellar mass. So even if those correlations do not tell us if disks evolve viscously or through winds, we can still use them to learn something about the parameters of the models. But really, if you want to understand what is the best way, whether disks evolve viscously or through winds, then the best way probably is to use actually disk radii, because that is the fundamental difference between the two frameworks. In the viscous one, the disk must expand with time, and in the MHD-WIN case, it must shrink. So that sounds very encouraging, at least from the point of view of the theory. From the point of view of the observations, actually, we are not there yet. And the reason is because most of the radii we have at the moment are dust radii. And as we all know, those are highly affected by radial drift that tends to move the dust to smaller radii. And so indeed, if you try to do this through models, and you compare models of viscous evolution with models on MHD-WINs, actually you get a similar shrink of the disk size with time. You don't really see expansion. And that's because radial drift dominates for the radii you can observe. This shrinking is actually observed in star-forming regions because the disks in upper SCO tend to be smaller than ones in Lupus and Chameleon. So dust radii are useful if you want to understand something about radial drift, but they're not useful if you want to learn about the way the disk evolves overall and what drives accretion. So the way to go forward there, of course, is the gas radii, where you sort of sidestep this problem. Though you still need to go through thermochemical modeling and use, other tracers of, for example, like CO, which is the most readily available, as we learned already in the previous talks. And here what we have at the moment is that the disks in upper SCO, also in the gas, tend to be smaller than in lupus. So if you were to interpret this at face value, this would actually be an indication for wind-driven evolution. But here I have to make really a strong caveat, because this is driven by the fact that, first of all, you have really small samples. And the other problem is that the samples we have come from really shallow observations. So for example, it could be that we missed a faint outer part of those disks, and so the real size of those disks could be larger. So this is still an open question at the moment. But thankfully, you should stay tuned for two large programs, AgePro and ECHO, that are serving now at the moment star-forming regions for many other things, but also one of the things that they will do is to measure gas radii for much larger populations. And so hopefully by the time of PP8, we will have a much better handle on the evolution of the gas radius. And with this, I give the word back to Megan.
Okay, so just to wrap up some takeaway messages, in terms of observations, we've seen very significant improvements in disk and star demographics since PP6. In terms of theory, the viscous framework can still work, but it's being increasingly challenged by the new observations that we've been getting. And on the other hand, the MHD wind framework is becoming a viable alternative. And if we want to dream big for PP8, we would advocate for something like D#, but including observations of CO for all the disks in the nearby star-forming regions. And then for the regions further away that haven't been as looked at in detail, to get them up to where the current demographics are for the nearby star-forming regions. And that's because in those more distant regions, you can't ignore things like environmental effects. So it's another dimension of understanding that we could gain. So thank you, everybody, for your attention, and we will happily answer your questions.
Thank you for a very wonderful talk. I'm sure we'll have some questions. Why don't we start over here?
Yeah, thank you very much. A really interesting talk and overview. I was wondering, wouldn't it be useful to look more at the early phases of disks? Because it's also quite possible that you have a scenario that you start with a viscous spreading phase to make the disk and to create the sizes, and then you deplete them magnetically. So could you get a constraint from that side?
Agreed.
Excellent. Nice short answers. That's what we're looking for. Over here.
Adele Plunkett, NRAO in the United States. This is probably related to the previous question. Is it that you have to either have viscous or MHD framework, or could there be even a combination of both in the same disk at the same time?
I mean, yeah, of course, there can be one. Of course, you can't discount. It's just that, you're trying first for the simplest explanation possible, where one of the two things dominates over the other. And, if we find that it's impossible to do that, then we will have to resort to combinations, yeah.
Okay, so I'm going to use the chair's prerogative to ask a same question a third time, which is when we talk about viscous and we think it's a global model, that doesn't seem right to me at all because the parameters change across the disk, presumably the same in the MHD wind. So how much are these just indicative, and that if you really need to do it, you've got to model everything?
I mean, I would tend to give the same answer I already given before. I mean, we are aiming first for the simplest explanation, but the hope is that what we get out in this way is some kind of average over, time scales and over radii. And if we need to make things more complicated, then we will do it.
Absolutely. Okay, so we'll go to the middle.
Okay. Takeru Suzuki from University of Tokyo. My question is on the theoretical model for the evolution of disk radius. I agree that if the wind-driven accretion is effective, the disk radii do not expand. But if the photoevaporation, particularly external source photoevaporation, is active, outer disk can be dispersed. In this case, the expansion radii does not occur. So do you have any good idea to distinguish these two mechanisms?
I mean, I absolutely agree with this. Actually, I have a PhD student working on this who is also here, so I invite you to look at her poster. But the thing to keep in mind is that some of the star-forming regions that we are looking at, like Lupus, Taurus, and so on, are regions where the impact of external photoporation is really low because the radiation levels are low. So hopefully those should be safe. I'm less confident about Upper Scorpius, to be honest. But yeah, there the thing to do is to look for similar regions where we can disentangle external photoporation from the inner mechanism of disk evolution, and then move to regions where external photoporation cannot be neglected.
Okay, thank you.
Excellent. And then to the back over here. Yes.
Hi, Giovanni. I was wondering if you also considered like the recent work from Xuning Bai that showed that even in non-ideal MHD simulations, you have the expansion of the protoplanetary disk. Then we also have seen talks about infall of gas during the evolution of the gas disk, and yeah. So I think we want to comment a little bit more on the caveats on considering the outer gas radius.
Yeah. So I would say that at the moment, what we again at face value, but what we see is actually shrinking of the disk rather than expansion. So, that already rules out all mechanisms that lead to expansion. But, we will reassess these in a few years when we'll have the data to look more at that. For what concerns accretion during the class 2 phase, I think that's an important open question. And I think there really the onus is on the observers to explore this, because as theorists we have an enormous parameter space to explore otherwise. And to tell us essentially how much accretion is still going on during the class 2 and how frequently this happens. And I think this is still an open question, and maybe that's something that I would also like to see solved by the time of PP8.
Excellent. Next. Yes.
Okay, thank you. Hiro Takami from ADA. I have a naive question about model disk evolution with viscosity and MHD weight. As we saw in previous talks, we've seen a variety of disk structures, and I assume you are not including them in the models because you didn't mention much in your talk. Then my question is, do you have to include them in the future? And if yes, would it possibly significantly change your model trend?
I mean, the answer is yes, absolutely. That's something that needs to be done more on the theory. I mean, some people are already doing it. That's clearly very important for what concerns the dust evolution, because it changes things completely, whether or not radial drift is unimpeded or whether you collect dust in traps. And actually, I encourage you to look, for example, at the poster by Luca De Lusso here that is doing this in disk evolution models. I'm less convinced this is important for the gas, because although you do expect to form pressure maxima, those are much shallower than the kind of traps you produce for the dust. So my I don't know, intuition would be that that's not that important for the overall gas evolution over a million-year time scale.
Thank you.
And up at the front.
Yeah, so I have a very naive question. I just wanted to know whether the size of the gaps, or let's say this, have any dependence on the fundamental properties of the disk that you are observing. Let's say the mass accretion rate, or let's say the mass of the disk. So is there any study done on that?
Sorry, the size of which gap?
The gaps and the rings, like you have different morphologies in this disk, right? So are they anyway related to the fundamental disk property?
I mean, absolutely they are. I mean, that's what we heard this morning from Mario's talk, because, depending on the different kind of instabilities and evolutionary processes, indeed, some of them tend to create substructures. But I don't think we're at the stage yet where we're trying to link what we are learning from overall global evolution models and apply it to the issue of substructure. But that's something to do in the future.
All right. Front.
Masahiro Ogihara from TDLI Shanghai. Thanks for interesting talk. And my question is related to the question by Takeru and Michiel. But you showed, you discussed the disk evolution using one model for wind-driven accretion. And, as you said, there are several different models for wind-driven accretion by, for example, Shuani or Takeru Suzuki or something. So I was wondering how robust your discussions are. So if you use different models, will your discussions change or not?
No, I don't expect them to change that much, because what we are lighting at the moment are really the qualitative differences, and those actually tend to agree between all the different formulations that people have done of wind models. You know, simple things like whether or not the disk should expand, the evolution of this depletion time scale, disk mass divided by accretion rate, those kind of things differ, of course, in the detail, but qualitatively tend to agree between the different models. So I'm quite confident that things will not change.
Excellent. To the back.
Thank you. Luna van Haastrecht, Leiden Observatory. I want to ask if you could comment on the potential bias that we have in making the medium disk lifetime compared to low mass stars and high mass stars. You might have seen the paper from Susan Vasser from 2022, where they show that low mass stars potentially have a factor 2 difference due to an overrepresentation of high mass stars in young distant clusters in the determination of these lifetimes. Could you comment on that?
Can you repeat that in a shorter way?
Sure. So currently our basically medium disk lifetimes have been determined by an overrepresentation from high mass stars in young clusters. And the question is, potentially low mass stars have a much longer disk lifetime. Could you comment on potentially that bias and what effect that would have on this?
Yeah, I mean, I think with the demographic surveys, you know, we covered all of the stellar masses down to the brown dwarf limit. So I don't know off the top of my head if somebody has done that sort of, you know, division of into different stellar mass bins and calculated the disk dispersal time. But you know, it's something that can be done now that we have this data, and it's across, it's unbiased in terms of sampling of stellar mass, at least for the nearby star forming regions.
Yeah, I think one of the wonderful things about your chapter is collecting all of this data for us. So
yeah, go download the table and make that plot during lunch.
Yeah, during lunch. Yeah. Thank you.
Hi, Geoffroy Le Sueur from Grenoble, France. Thank you for the very nice talk. I wanted to go back to the idea of disk shrinking because of MHD winds. I think that most of the literature on MHD disk winds is actually focusing on power law disks, in which there is no outer boundary, with the notable exception of this paper by Young and Bai. If you now look at what's happening for an MHD disk wind at the outer radius, an MHD disk wind is powered by the accretion energy. There is no such accretion energy at the outer radius because there is nothing to accrete. So you can't drive an MHD disk wind at an outer radius, and this has been shown in this paper by Young and Bai. So I don't think that the dynamics of MHD disk wind support the idea that a disk should be shrinking if it was driven only by MHD disk wind. So that's one thing. And the other thing is that, as we've heard from Mario's talk this morning, we know that MHD disk winds are driven by the magnetic field strength, and we know that the magnetic field strength should decrease by orders of magnitude during the lifetime of the disk. So it means that the efficiency of MHD disk wind should decrease dramatically as they evolve. So I'm not quite sure this is included in these models, but I mean, do you think like you could have constraints on how strongly the field should evolve as time goes on from these models or not? Or is it like a prospect for future work?
I mean, it's definitely something to explore in the future, but yes, those constraints can be have. Because, I mean, the reason is because depending on how the magnetic field changes with time, then you get a different evolution of the depletion time scale of the field, of the disk. And that's something you can measure because you can measure mass accretion rates and disk masses. So if you map how this changes with time, actually you can get a handle on that. And regarding the first point, I'll take your word and deflect this problem back to you guys doing MHD. But I'm looking forward to see the developments.
Excellent. Over to you.
Hi, okay. Nagayo Shohachi from the AGI Taiwan. So even though you have been, mostly focusing on the class 2 type of disks, I would like to emphasize the importance of the class 01 disks as well, including evolution. So I was just wondering, when we think about the evolution from a class 01 to disk to class 2 disks, whether your whatever model can be simply applied, or you do need a lot of modification to think about such evolution from the early phase to the late phase.
So it does need to be modified because clearly you will still have the info. So that's something to be taken into account.
So you can simply apply the same scenario.
Yeah, but you need to know how the info changes with location in the disk, with time, and so on. And so that's the information, the additional information to put in, for example. And of course, then you need more input from the observations. Program like eDisks and these kind of things that will tell us how disks are at the young stage of class zeros and class ones.
Okay, thank you.
All right.
Sierk van der Wischa, MPIA. So there's this wonderful saying about how the world looks like when all you've got is a hammer. And actually, if you think about upper SCO and the things you've been saying about upper SCO from the perspective of external photoevaporation in intermediate external UV fields, like 10 to 100 or so, it looks eerily like that might matter a lot. And then you get this issue that you have this sort of linchpin for what disks looks like when they're 5 to 10 mega years old, right, and disk populations. My question to you, I guess, is what should we look at if maybe we don't trust that upper SCO is such a good probe of internal disk evolution processes? Should we look at debris disks more, which I know you did discuss in the chapter? Should we look at other regions?
I mean, so if upper SCO isn't as safe from things like external evaporation that we think of, I actually think that might be a good thing, because one of the problems with these surveys of nearby star-forming regions is that we have all these young ones, and then we have nothing, and then we have upper SCO. But if you go a little bit further out, so we didn't cover this in the chapter, but we've used ALMA to look at Sigma Orionis and Lambda Orionis, which are right in the middle of that age gap. And so, you have to consider things like external photoevaporation, but, there's obviously internal processes too. So it won't be Giovanni's ideal situation of doing the simplest thing first, but we can actually get regions surveyed that actually have a more smaller resolution in terms of age. So I think it's not necessarily a horrible thing.
Thank you. So we've got 3 minutes left and 3 speakers. If we can do a minute a speaker, we'll get through this. Thank you.
Enrique Macias, ISO Germany. So thank you for a nice chapter and talk. So we're looking at these trends of disks with age, but also disk fraction evolves with age, and presumably or naively I would assume that disk fraction doesn't necessarily evolve the same across stellar masses or disk masses. So do we need, or can we take this fraction into account when we're analyzing these demographic trends? And I'm thinking on things, for example, of Hughes being young and having lower masses, or on the one hand, and the other hand, the steepening of the disk mass versus stellar mass with age.
Yeah, I think that's something that would be interesting that hasn't been looked at too in detail. Another thing that's sort of related to this question and the previous one is that these plots of cumulative distribution and things like that showing the differences in the dust mass population, they don't take into consideration the differences in the stellar population, right? And if there's a dependence on disk mass and stellar mass, then you're going to see differences that aren't necessarily related to the actual, material in the disk. So, yeah, I think that would be an interesting thing to look into for sure.
Excellent. Over here.
To tie on to the question regarding the stellar mass dependence, how high above the one solar mass would you say that your statistics don't suffer from low number statistics? In other words, when do you get worried about extrapolating beyond, say, 1.2? Is that a realistic guess? And for PP8 goals, do you think we will improve the situation in that sense?
So yeah, there are, most of the stars in the galaxy are M dwarfs, so there's not that many at the higher mass region, the higher stellar mass points. Hard to say about improvement because the population is what it is, besides just getting more regions surveyed, but we're going to hit a limit at some point. So I'm not sure if there's going to be huge differences by the time we get to PP8, but yeah.
But where would you draw the limit, basically, is my question.
I don't have a answer for that off the top of my head, but we can look at the plots that show it. So yeah, you can see there's not that many, right? Especially as you get to like older regions and things like that. So, you know, I think around 1 solar mass is a good place to say, you know, things look pretty good. After that, it's a little uncertain. And there's also been work, I know, on whether or not this is actually 2 power laws. So there'll be a break, and I think it is around 1 solar mass as well. I think it's by Atkinson, 2019, if you want to look into that.
Thank you.
All right, so we are really, really short, please.
Okay, a really short question. This is Shangjia Zhang from University of Nevada, Las Vegas. And a wonderful talk, and I have a question for Megan on the dust mass estimates. These mass are estimated from the wonderful results from ALMA, but even pre-ALMA, you can estimate the dust mass from SED feeding. And I have a feeling that for the SED feeding, you have observing many wavelengths and opacity, you suffer less uncertainties in the opacity at the single wavelength. So actually, it can be a better estimate or not. I'm not familiar with this specific things. Can you comment on that?
I'm not an expert in that area, so I'm sorry I can't comment on that.
Okay,
but, yeah.
thank you.
But thank you.
All right. Remember, there's going to be a picture taken, so please don't move. But let's thank the speakers. And let's thank all of the speakers.